Hello everyone, my name is Ke Wang. I'm from the Robot Intelligence Lab, Imperial College London. Today I will present my IROS work, Design and Control of Slider, an ultra-lightweight, nearly low-cost bipedal walking robot. Here is the overview. I will first talk about the background, bipedal robot design. Then I will talk about the details of design of slider, the control of the slider. Then I will talk about the experimental results of slider working in simulation and in reality. Most of robots adopts the anthropomorphic design, as can be seen in the right. It has 5 or 6 degrees of freedom in each leg. It has pitch, roll, and sometimes yaw on the hip, pitch on the knee, pitch and roll on the ankle. However, the knee joint has several disadvantages. Normally, the robot walks with bent knees because of the inverse kinematics singularity. Therefore, it requires more high torque on the actuators. The mass of the knee contributes significantly proportion to the leg of mass, and therefore it consumes excess power for the hip joint. Is it possible to design a walking robot without knees? The answer is yes. So we propose a non-anthropomorphic design, which replaces the knee joint with a prismatic joint at the hip, which can be seen on the right. With this design, the mass is concentrated closer to the body, and it eliminates the excess power consumption from the bent knee walking. The drawbacks is it complicates the hip mechanism. So here is the overview of slider. It has 5 degrees of freedom in each leg. The mass is concentrated at the hip, so the legs are ultra lightweight. It has a total mass of 15 kilograms, with a height of 1.2 meters. We specifically designed it to be produced in-house, so most of the parts of the gearbox are 3D printed. Also, it has a very low cost of manufacture, which is less than 10,000 pounds. It has low cost sensing with 4 force sensors on each foot and motor encoders on each joint. The prismatic joint, we call the slide joint, is the main part. So we use the servo belt mechanism which converts rotational motion to the linear motion. The mechanical details can be shown below. Another difficulty in manufacturing is the hip joint. The hip joint always requires high output torque, and most robots use harmonic drives. However, harmonic drives are very expensive and very hard to manufacture in-house. Instead, we designed our own low-cost cycloidal gearbox, which can be 3D printed in-house. Below is the design details. We compare the sliders design with the most common anthropomorphic design in terms of workspace. So the first column shows that slider is not good at passing a narrow corridor. However, as can be seen from the second column, slider is good at stepping over steep obstacle or stairs. While the anthropomorphic robots has difficulties because it has knees. Also, slider can take a larger step than anthropomorphic design because the anthropomorphic design works with bent knees. We compare these two designs also in terms of the mass distribution. As can be seen from the left, is the mass distribution of these two different designs. Here we use Coleman robot as an example of the anthropomorphic design. As can be seen, the right balls represents the approximate center mass of each link, and the size of the blue ball represents the value of the mass. The red ball represents the center of mass. We can see very clearly that the legs of slider are considerably lighter than the anthropomorphic robot Coleman. Also, the center of mass of slider is much closer to the body. Slider fits the linear inverted pendulum model much more closely. Another way to compare the lightweightness is the height versus weight ratio. On the right plot, we can see the horizontal axis is the mass, while the vertical axis is the height. We collected the data of different bipedal and quadruped robots from the published paper or the website of the product. The higher the height to weight ratio is, the more lightweightness is the robot. As we can see, slider has a high height-weight ratio, which shows that slider is more lightweight than most of the bipedal and quadruped robot that is existed. We also compared the center of mass movement between slider and Coleman. We let both robots work with the same gait. As can be seen in the right, is the center of mass movement. The right top is the center of mass movement in the x-y plane, and the right bottom is the center of mass movement in the xz plane. We can see clearly that the center of mass movement of slider varies less than that of the Coleman, which indicates that in xy plane slider exhibits less sway, and in xz plane slider deviates from the constant height less. For the control of slider, the controller of slider is given the center of mass average velocity as a reference. Then it uses a preview controller with a linear inverted pendulum model to generate the gait. To compensate for the backlash in joints, we have a feed-forward trajectory compensation. When the robot is walking, we use the center pressure feedback to stabilize the robot. Here shows the slider walking in gazebo simulation. We also showed slider walking in real world. On the left is the slider walking without compensation nor center of pressure feedback. On the right shows slider walking with feed-forward compensation only. As the video showed, without compensation nor center pressure feedback, the real robot can only work very few steps. While with feed-forward compensation, the robot can walk several steps. However, it will deviate from the reference trajectory more and fall down eventually. Now we show the real robot experiments with feed-forward compensation and center pressure feedback. It works quite stably. Thank you for watching.